So now, after having discussed the three boundary conditions, for the three cases, in fact the two boundary conditions for the three cases, let's start deriving the temperature distribution and fin heat transfer rate for each of the three cases. The first case would take a little bit of time, but the second and the third cases would be solved in no time. The case A, which is the general case, says that at the tip of the fin, the heat which has been conducted till the tip of the fin is convected away by the surrounding fluid via convection. So minus Ka times d theta by dx at x is equal to L was HA times Ts minus T infinity, and we had then written that T minus T infinity as theta, and areas had got cancelled out. So d theta by dx at x is equal to L would be h theta upon k minus h theta upon k. So now what we would be doing in each of those three cases is that we would be starting with this equation A, which is the general form of that solution. And in this solution there are two unknowns, C1 and C2. So we would be putting both of the two boundary conditions, both the boundary conditions in here to find out C1 and C2. And once we find out C1 and C2, we will put those expressions for C1 and C2 in A to get theta as a function of x or temperature as a function of x. So if we put the first boundary condition in equation A, the first boundary condition says that where x is 0, theta has a value of theta b, and theta is in fact the temperature at any x minus T infinity. So theta at base means temperature at base minus T infinity. So theta would be theta b, and in place of x we will write 0. So e to the power 0 would become 1. So the right hand side of the equation would therefore be C1 plus C2. Now the second boundary condition, which has been written over here, is on d theta by dx. So what we need to do is we need to differentiate equation A so that we get d theta by dx, and then we would be able to apply the second boundary condition. So if we differentiate equation A, the left hand side would be d theta by dx, and it would be at x equal to L. Why? Because the second boundary condition is at the tip of the fin, is C1 e to the power mx. So C1 would remain C1. The differential of e to the power x would be e to the power x, means e to the power minus mx, and the differential of mx would be m. Similarly, the differential of second term would be C2 and then e to the power minus mx times minus m, and of course at x equal to L. Now the second boundary condition says that d theta by dx at x equal to L is minus h theta over k. So on the left hand side, in place of the left hand side, we can then put minus h times theta over k. Theta L means theta, it's not theta into L, rather it is theta at x is equal to L, means at the tip. And the right hand side remains unchanged. All we have done is that we had put L in place of x, because this differential has been evaluated or will be evaluated at x is equal to L. So wherever we see x, we will write L in its place. Now the left hand side, which is minus h theta over k, so in place of theta, we will put C1 e to the power mx plus C2 e to the power minus mx, which is equation A, and since it is being evaluated at x equal to L, so in place of x we will write L. So C1 e to the power mx means ml plus C2 e to the power minus mx means minus ml, and m has been taken common out of the right hand side, and then it has been brought into the denominator of the left hand side. So minus h over mk times C1 in place of C1 we can write theta b minus C2 using equation 1. And C2 would remain C2. So what we are going to do over here is that we are going to write C1 in terms of C2, so that we would have an equation in terms of C2 only, where we will find out C2 from. And then C1 on the right hand side will again be written as theta b minus C2, and the rest of the things remain unchanged. Now we need to multiply this h over mk on inside. So we would be having 3 terms inside, and then we would also be having 3 terms on the right hand side. Since we are trying to find out C2 from here, so we will group together, C2 terms on the left hand side of the equation and non C2 terms on the right hand side. So we have brought all the C2 terms on the right hand side of the equation. 2 were already there, and these 2 have been brought on the left hand side, so they would then bear a negative sign. Now it says C2 e to the power minus ml. This thing has been written over here, and then C2 e to the power ml, which has been written over here. And then there are 2 h over mk terms. So see, there are 2 non h over mk terms, and there are 2 h over mk terms. So we are writing the 2 non h over mk terms together, and then we are writing the 2 h over mk terms together. On the right hand side, theta b can be taken common out of these 2 terms, and e to the power ml can be taken out of these 2 terms. So we would have 1 plus h over mk within the bracket. Now from these two non C2 terms, non h over mk terms, we have taken C2 out, so it would be e to the power ml plus e to the power minus ml. And from these 2 terms, which are h over mk terms, so we have taken h over mk common out and C2 common out as well. So we would have e to the power ml plus minus e to the power minus ml. So therefore from these 2 terms which are there on the left hand side, if we take C2 common out, so and whatever is left is taken into the denominator of the right hand side, so we would have this as the value of C2. On the right hand side, in the numerator of the right hand side, we have theta b, we have EML, we have 1 plus h over mk, and then the rest of the things which were there on the left hand side of the equation have been taken into the denominator of the right hand side. So this is the expression for C2. See, we do not have C1 over here, we do not have T over here, we do not have X over here. All the parameters are in fact constant quantities. Now we can put this value of C2 in 1 to get C1. See, equation 1 was that theta b is C1 plus C2. So now we can write C1 as theta b minus C2, right, in this form. And then theta b minus C2 can be written as theta b minus whatever C2 is, whatever we have found out on the last page. And then we can write, and then we now need to solve it. So out of these 2 terms we can see that there is theta b over here. So if we take this theta b common out of both these terms, so it would be 1 minus this whole thing except theta b. And then if we take the LCM, so all this thing which is here in the denominator will be multiplied with 1. So we will have EML plus E minus ML plus H over MK EML minus H over MK E minus ML, and then whatever we have on the in the numerator over here. So it would be minus EML and then minus EML H over MK. Now some things would get cancelled out. For example, e to the power ml would get cancelled out, and h over mk e to the power ml will also get cancelled out. So we would be left with two terms only, e to the power minus ml minus h over mk e to the power minus ml, which has been written here in the numerator. So if we take e to the power minus ml common, we would have 1 minus h over mk times theta b over the denominator. Now you can see the similarity between C1 and C2. And what is that similarity? If you see, C2 is same or similar to C1 with the difference that in the numerator we had e to the power plus ml and over here we had 1 plus h over mk, right? And the denominator is still the same. The denominator is the same. So after finding out C1 and C2, we will put those expressions of C1 and C2 in equation A to get theta as a function of x, or in fact temperature as a function of x. So equation A was that theta x is C1 e to the power minus mx. So this is C1, which is being multiplied with e to the power mx, plus C2 e to the power minus mx. So this whole thing is e to the power C2, which is being multiplied with e to the power minus mx. Now we have e to the power minus ml times e to the power minus mx. So they would be multiplied with each other, and then those powers would get, those exponents would get added up. So it would be minus ml plus mx. But we will take minus m common out so as to write it as L minus x. See, why L minus x? Because x would either be less than the length of the fin, or at most it would be equal to L. So therefore it's a way to remember that we need to write the large quantity minus the smaller quantity, for which we need to take minus m common. And the rest of the things remain unchanged. It is 1 minus h over mk, and what we are doing in the same step is that we are taking this theta b common out of the numerator of the two terms, and we are taking that theta b into the denominator of the left hand side of the equation. Now over here it is e to the power ml times e to the power minus mx, so it would be ml minus mx. So we will take m common out so as to have L minus x within the bracket. Now we will multiply e to the power minus ml minus x with these two terms, 1 and h over mk. So we would have these two terms, which are the first two terms in the numerator, and then we will multiply this with the bracket terms, two terms in the bracket. So it would be eml minus x plus h over mk eml minus x, and at the same time we have taken the LCM. So the good thing over here is at least the denominators are the same. At least the denominators are the same. So therefore we would have the same LCM, and nothing would be multiplied from the denominator into the numerator. Now in the numerator there are four terms, two of which are h over mk terms and two of which are non h over mk terms. So we will bring together the non h over mk terms, which are e to the power ml minus x plus e to the power minus ml minus x, and we will bring together h over mk terms as are as they have been brought over here. So what we would be doing then is that we would be doing we would be dividing the two terms in the numerator, which have been expressed in the square brackets, and we will also be dividing the two terms which are there in the denominator by 2. So everything, the whole numerator and the whole denominator will be divided by 2. So if we then compare this particular form with this expression written over here, which is regarding cos hyperbolic x. So what is cos hyperbolic x? It is e to the power x plus e to the power minus x by 2. So in fact over here we have got the same form, e to the power something plus e to the power minus the same thing by 2. So it would be cos hyperbolic of whatever is there in the exponent, which is m times L minus x, cos hyperbolic of m times L minus x. plus h over mk, this thing, and the only difference between this one and this one is that of the negative and positive sign in between the two. Over here we had this positive sign, and over here we have this negative sign, and that is the only difference between cos hyperbolic x and sine hyperbolic x. Sine hyperbolic x is e to the power x minus e to the power minus x by 2. So we have e to the power something minus e to the power minus the same thing by 2. So it would be sine hyperbolic of whatever we have in the exponent, and what we have in the exponent is ml minus x. So it would be h over mk sine hyperbolic of ml minus x. And similarly the denominator would be cos hyperbolic of ml plus h over mk sine hyperbolic of ml. It means that this theta, see, we can write this theta as t minus t minus t infinity, and we can write this theta base as t base minus t infinity. So out of t infinity and tb, what is, see, tb is constant and t infinity is constant as well. So what is the only variable on the left hand side? It is t. So which is there in theta. So theta, and what do we have on the right hand side? M is constant, L is a constant quantity. See, total length of the fin is a constant quantity, and M is also a constant quantity because that was hp over root of hp over kc. K is a constant quantity. So all the things on the right hand side are constant quantities except x. So this equation is in fact relating temperature with x, and we have got x at various places, in fact to a couple of places. So in fact this equation is in fact the temperature distribution. Why? Because it is relating the temperature with x. And what is x? X is all along the length of the fin. For example, x is equal to 0 means we are talking about the base of the fin, or x may be L by 2, or x may be L by 4, or x may be 3L by 4, or x may be equal to L. So x would assume different values. So x is a variable. The minimum value that x can have is 0, and if it is 0 we would be talking about the fin base, and the maximum value that x can have is equal to the length of the fin, and if x is equal to length of the fin, over here we would be talking about the tip of the fin. So if we put x, so then over here t would be the temperature at x is equal to 0. If we put over here x as 0, so we would be talking about the temperature at the base. If we put x as L over here, we would be talking about the temperature at the tip of the fin. So this expression is in fact the temperature distribution. Now are we finding out the temperature distribution for the very first time? Are we finding out the temperature distribution for the very first time in chapter number 3? No. See, we have found out the temperature distribution in the case of plane wall, in the case of cylindrical coordinate system, in the case of spherical coordinate system, and now we are doing the same thing for the case of fins. So temperature distribution was linear in the case of plane wall. It was logarithmic in case of cylindrical coordinate system, and it was, as I did not derive it, but I had derived 2 for you, and I had then asked you to derive the third one on the same lines, which was 1 over 4 pi k times 1 over Ri minus 1 over R naught. It was in fact the thermal resistance. And the temperature distribution in case of fins is in fact hyperbolic. One more thing that you should realize, that over here the numerators and denominators are exactly the same with the difference of x. If you write the denominator without x, if you write the numerator without x, it will become denominator. If you write the numerator without x, it will become denominator. So if you are given the numerator and you are asked to write the denominator, all you need to do is get rid of x. That would be the same as denominator. Why I am focusing upon those tricks? Because in the end I would be telling you how you do not need to get afraid of those lengthy expressions, and how you can very easily remember this expression and other expressions by heart without facing any problems. Now the second thing is the fin heat transfer. See, fin heat transfer rate, which is denoted by QF, is in fact, first of all, try to understand what it is. Fin heat transfer rate is the heat transfer that will be made by the fin, means how much heat is being transferred by the fin. And fin, how much heat will be transferred by the fin? Fin will transfer the same amount of heat as it will come into it if the system is working under steady state conditions. Of course, fin will not transfer more heat than is coming in, that is out of question. And unless there are some sort of special arrangements or this and that, and fin will not transfer less heat than what is coming in, because if it does so, there will be energy storage in the fin and the system will no longer be under steady state conditions. So over here we would be considering steady state conditions, means the heat transfer from point A to B would be the same as that from B to C, and between any two sections it would remain the same. So what is fin heat transfer rate? Fin heat transfer rate is the rate or amount of the heat transfer made by the fin. And how much heat would the fin transfer? It will transfer the same amount of heat as the heat that will come into it. Now where the heat is coming into the fin from? Where the heat is coming into the fin from? It is coming into the fin through the base. Via what would be the mode? How the heat will be crept into fin from the base, will come from the base into the fin. What would be the mode of heat transfer? Of course it would be conduction. So therefore fin, in order to evaluate fin heat transfer rate, we will write the conduction expression, Fourier's law of heat conduction, minus K dt by dx at the fin base, means at x equal to 0. This is the heat which is coming in from the base into the fin, and then the same heat will be transferred throughout the fin. And then we can write this dt by dx as d theta by dx. Again, we are not writing t as theta because t is not equal to theta for the reasons mentioned before. So over here we are writing dt by dx as d theta by dx because theta is t minus t infinity, out of which t infinity is a constant quantity. Therefore differential means d theta by dx would be same as dt by dx. So over here it says that we need to differentiate theta with respect to x, right? We need to differentiate theta with respect to x. It means we need to have theta as a function of x, right? If you want to differentiate y with respect to x, you need to have y as a function of x. So if we want to differentiate theta with respect to x, we should have theta as a function of x. And where do we have theta as a function of x? This is theta as a function of x. So we need to put this expression over here. See, theta b will come over here and then from the denominator into the numerator of the right hand side, and then cos hyperbolic of ml minus x plus h over mk sine hyperbolic of same thing. See, whatever is written here, ml minus x is written over here as well, right? And then the denominator is the same as the numerator without an x. So we need to write this whole thing over there. So see, we have got so therefore QF is minus K dy dx of theta. And what is theta? This whole thing is theta. Theta b times cos hyperbolic of ml minus x plus h over mk sine hyperbolic of same thing ml minus x. And then the denominator is the same as numerator without an x. So minus k AC, and then theta b can be taken out because because since we are differentiating with respect to x and theta does not have x, theta is simply tb minus t infinity. So now we need to differentiate whatever is written in the square brackets with respect to x. See, over here it is not u upon v differentiation because we do not have x in the denominator. X is without denominator. So we would only be differentiating numerator. X would serve as a coefficient. x would serve as a coefficient. So sorry, the denominator would be served as coefficient. So therefore the denominator would be written as it appears. It is only the numerator which will be differentiated with respect to x. Now differential of cos x is minus sin x and differential of sin x is cos x, but in case of hyperbolic the sign does not change. Differential of cos hyperbolic x is sin hyperbolic x without a negative sign, and the differential of sin hyperbolic x is cos hyperbolic x. So the differential of cos hyperbolic x is sin hyperbolic of x, and then differential of, we need to differentiate m times l minus x as well. So the differential of ml would be 0 and the differential of minus mx would be minus m. Similarly, h over mk would remain h over mk. Differential of sin hyperbolic x would be cos hyperbolic of whatever x is, and then the differential of ml would be 0 and the differential of minus mx would be minus m. Now we can take minus m common from these two terms, and then minus m would come out. So minus and minus would become plus, we would have m, and we have k times area times theta over there as well, and then what we would be left with in this square bracket, we would have sin hyperbolic of m l minus x, and since this differential is being evaluated at the base, means at x equal to 0, so wherever we have x we will put 0 over there. So it would be sin hyperbolic of ml, plus h over mk cos hyperbolic of ml minus 0, means cos hyperbolic of ml, and the denominator remains unchanged. Now this m is in fact root of hp over kac. M is in fact root of hp over kac, right? So this kac over root of kac would become root of kac. 2 over root 2 is root 2. So therefore under the root sign we would have hp kac, and theta b remains theta b over here, and whatever is written in the bracket remains unchanged. It would be sin hyperbolic of ml plus h over mk cos hyperbolic of ml, and the denominator remains unchanged right from the very start. So this is the expression for QF. See, there is no x in here. As we had an x in the case of temperature distribution, we do not have any x over here. Why? Because over there it was temperature distribution. It was temperature as a function of x. Temperature would have various values at various values of x. What is Q? It is the total heat which is being transferred from the fin. So that is why it does not have x in it. It will give us a particular value, let's say 200 watts. So from the fin 200 watts would be transferred to the surrounding fluid. Now that was for case A. Let's do the same thing for case B, but it would not take that long. Case B was the case of insulated tip, and these were the two boundary conditions, right? So we would be doing the same thing over here as well. Means we will start with equation A, which is the solution to that differential equation, which is c1 e to the power mx plus c2 e to the power minus mx, and then in this particular equation A we would be putting in the two boundary conditions one by one so as to find out c1 and c2. So now since the boundary condition 1 is the same, so we will get the same result as we got in case A. Means that theta is theta b where x is 0, means at the fin base. So in place of theta we will write theta b, and it would be c1 e to the power 0 plus c2 e to the power 0. So it would be c1 plus c2 on the right hand side of the equation. Now the second boundary condition, which says d theta by dx at x equal to L, means at the tip is 0. So we need to first differentiate equation A so that we can get d theta by dx, and then so that we would be able to apply the boundary condition which is related to d theta by dx. So if we differentiate the equation A, we will get d theta by dx on the left hand side as c1 differential of e to the power mx would be e to the power mx times m, and that is the same thing that we did in case A. And then c2 would remain c2 differential of e to the power minus mx would be e to the power minus mx times minus m. and since the second boundary condition is at the tip, so all the things would be evaluated at the tip. So therefore this d theta by dx is at x equal to L, and this would also be at x equal to L. Now what is the second boundary condition? Second boundary condition says that d theta by dx at the tip is 0. So therefore this d theta by dx at x equal to L would be written as 0, right? Would be written as 0. And the right hand side would remain unchanged, with the only thing that we will write L in place of x. We will write L in place of x. So it would be mc1 e to the power ml minus mc2 e to the power minus ml. And then c1 m will get cancelled out throughout, so c1 e to the power ml would be c2 e to the power minus ml. So therefore c2 can be written in this form: c1 e to the power ml upon e to the power minus ml. So it would become e to the power ml times e to the power ml, means e to the power 2 ml. So this would be the expression for c2 in terms of c1. Now if you put this in 1, and 1 says that theta b is c1 plus c2, so therefore c2 can be written as c1 e to the power ml. So now we have got only c1. So if we take c1 common, it would be 1 plus e to the power 2 ml, and we need to take that thing into the denominator of theta b. So therefore c1 would be theta b upon 1 plus e to the power 2 ml. Therefore after finding out c2, we can then find out, after finding out c1, we can then find out c2 from here. c2 is c1 e to the power 2 ml. What is c1? This thing is c1, which is being multiplied with e to the power 2 ml as is written over here. So now this e to the power 2 ml may be taken over here into the denominator of 1 plus e to the power 2 ml. So 1 upon e to the power 2 ml would be e to the power minus 2 ml, and this thing upon the same thing would become 1. So therefore c2 would be theta b upon 1 plus e to the power minus 2 ml, e to the power minus 2 ml. So these are the expressions for c1 and c2, which we have found out in no time. And if you consider the time that we had spent while finding out c1 and c2 in case A, you would realize that this case has been solved in about 5 minutes or so, right? So now we will be putting those c1 and c2 in A back to get temperature as a function of x or theta as a function of x. So this is c1, which is being multiplied with e to the power mx, and then we have this as c2, which is being multiplied with e to the power minus mx, right? So from these two terms we can take theta b common out, and then that theta can be taken into the denominator of the left hand side. So the left hand side would become theta over theta b, or theta x over theta b is the same thing. And then we would have e to the power mx over 1 plus e to the power 2 ml plus e to the power minus mx over 1 plus e to the power minus 2 ml. Now see, we had written that temperature expression in the form of e to the power ml minus x in case A, right? Over here you will realize that we have got e to the power mx, but there is no ml over there. So what we will do over here is that we will multiply and divide by e to the power ml or e to the power minus ml, depending upon what is required. So over here, if we this negative term, it is e to the power mx plus mx, so it will be multiplied with negative thing, and over here it is e to the power minus mx, means it is negative, so it will be multiplied with positive exponent. Positive exponent will be multiplied with negative exponent, and negative exponent will be multiplied with a positive exponent, and it will be divided with the same quantity, same term. Now e to the power mx plus ml, e to the power mx minus ml. So what we need to do is that we need to write it in the same form as we had discussed over there, means L minus x. So in order to write it in the form of L minus x, minus m needs to be taken out. Minus m needs to be taken out, which is the coefficient of L, which is the multiplier of L. And then over here m will be taken out so as to write it in the form of L minus x. Now again, the denominators of both the terms are in fact, of course, this e to the power minus ml will be multiplied with 1 to get to yield e to the power minus ml, and this e to the power minus ml will be multiplied with e to the power 2 ml. So 2 ml minus ml will give us 1 ml, and similarly 1 multiplied by e to the power ml would be e to the power ml, and e to the power minus 2 ml plus ml would be minus ml, right? So again the denominators are the same. So upon taking the LCM, we would have the same two terms in the numerator that are written over here. And now if we do the same thing, it means that we divide the whole numerator and the whole denominator by 2. So we can then write e to the power minus x plus e to the power x by 2 as cos hyperbolic of whatever that x is, of whatever that exponent is, over cos hyperbolic of ml. And what is this? It is theta over theta b. And what is theta? T minus t infinity, out of which t is the variable, and theta b is t base minus t infinity. Both are constants. So again this expression is nothing but the temperature distribution, means temperature as a function of x, means temperature as a function of x. So do you see any difference between the first case temperature distribution and the second case temperature distribution? If you compare the two, you will realize that longer expression has been reduced into half. The second term is not there anymore. In fact, it has been reduced to half, and that is the advantage of assuming that the tip is insulated, whereas I had explained earlier that it is not really insulated. Now for the heat transfer, fin heat transfer rate, again it would be minus Ka d theta by dx at x equal to 0, for the reasons that I just explained in the previous case. So the fin heat transfer rate would be minus Ka times d by dx of theta, and theta is this whole expression which we have just derived on the previous slide. So again it is not the case of u over v differentiation, because we do not have x in the denominator, rather we have x in the numerator only. So the differential of cos hyperbolic x would be sine hyperbolic of this thing, and then differential of ml would be 0, and the differential of minus mx would be minus m. So this m would be taken outside, so this negative and negative would become positive, and we would have m k ac times theta b times sine hyperbolic of ml minus x, and this differential will be evaluated at the base, means at x equal to 0. So wherever we see an x, we will put 0 against it. So it would be sine hyperbolic of ml over cos hyperbolic of ml, which can then be written as tangent hyperbolic of ml. And then m can be written as root of hp over kac, and this kac over this kac over root of kac would be equal to root of kac. Just like I told you before, that 2 upon root 2 is in fact root 2. So under the root sign we would have hp kac theta b times tangent hyperbolic of ml. Right? So this is the fin heat transfer expression for the insulated tip case. Now let's take the third case, which is that of the long fin, and these are the two boundary conditions that we have already discussed before. So now all we would be doing is that we would be putting those boundary conditions in equation A. So for the first boundary condition, which has been the same as in the last two cases, so we'll get the same result, theta b is c1 plus c2. However, while applying the second boundary condition says that at the fin tip, means at x equal to L, when x becomes very large, theta would approach 0, because when x would become very large, temperature at the tip of the fin would approach T infinity, and therefore theta would approach 0. So if you put that second boundary condition in equation A, theta would be written as 0, c1 e to the power infinity plus c2 upon e to the power infinity. E to the power minus ms can be written as 1 over e to the power mx, and then e to the power infinity. Now 1 over e to the power infinity means 0. 1 over infinity is 0, so C2 upon infinity would be 0. So therefore it would be 0 as C1 times infinity. Now we are not considering this as one of the 7 indeterminate forms that you have learned earlier, probably in first year of engineering. Rather, we are going to solve it using a very simple logic, and that logic is that if C1 is being multiplied by a very large number, the answer is 0. If C1 is being multiplied by a very large number, infinity, then answer is 0. It means that C1 is itself 0. It means that C1 is in fact itself 0. Right? So therefore C1 would become 0, and therefore when C1 becomes 0, equation 1 would imply that C2 is theta b. C2 is theta b. See how quickly we have found out C1 and C2, which took a little bit longer time in case B and a long time in case A. Now all we need to do is put both C1 and C2 in equation A to get theta as a function of x, means temperature as a function of x. So it would be C1 means 0, so the first term would become 0, plus C2. C2 is theta b, C2 is theta b times e to the power minus mx. So theta over theta b would be e to the power minus mx. This is in fact the simplest temperature distribution out of the 3 cases. And then for the fin heat transfer rate, again it would be minus k d theta by dx, which will be evaluated at the base, means at x equal to 0, and it is d by dx of theta, and theta is theta b e to the power minus mx. So it would be differential of e to the power x is e to the power x, so it would be e to the power minus mx, and then differential of minus mx would be minus m. So minus and minus would become plus, and then it would be kac theta b times m, and then e to the power minus mx is being evaluated at x equal to 0, so therefore e to the power 0 would be 1. So therefore this exponential term will no longer be there in the fin heat transfer rate. Now m is root of hp over kc, and kc over root kc would give us root kc. So in the root sign we would have hp kc times theta b. So that would be the expression for the fin heat transfer rate. Now let's summarize the 3 cases. And this is a very important page, important and interesting, because you should learn how to keep track of those 6 expressions. And what are those 6 expressions? Temperature distribution and fin heat transfer rate for the 3 cases. So T and Q for case A, temperature and Q for case B, and temperature and Q for case C. See, it starts with cos hyperbolic. So what may be confusing for you, because you might tend to forget whether it was cos hyperbolic first or sin hyperbolic first. So see, does C come first or S comes first? It is C which comes first. So the expression would start with cos hyperbolic. The expression would start with cos hyperbolic of ml minus x, cos hyperbolic of ml minus x, right? Plus h over mk sin hyperbolic of the same thing, plus h over mk sin hyperbolic of the same thing, means ml minus x. So you would be able to write the numerator. And how would you write the denominator? The denominator is exactly the same as the numerator without an x. So if you get rid of the x in the numerator, it will become the denominator. So this is how easily you can write theta over theta b by yourself, right? And what happens in case B? See, this half just vanishes away. It is not there in insulated tip case. So it is cos hyperbolic of ml minus x over cos hyperbolic of ml. This is how easily you can write the temperature distribution or theta over theta b for the insulated tip case. See, there is nothing to remember in long fin case because it is simply e to the power minus mx, right? So there isn't any long expression that you would think that how would you be able to keep track of it. Now when it comes to the fin heat transfer rate, see, this root of HP KAC has been written as capital M in our book. But that M is not mass. It has been written as capital M, right? But you will realize that this root HP KAC theta B is there in all the three terms. In all the three terms, right? And see, where did we come up with those expressions of QF from? We wrote QF as minus Ka d theta by dx. And where did we brought theta from? From here. Right? So therefore we have got this theta b in here. This is why we have got this theta b in here. It is coming from theta over theta b. And then and that d theta by dx was we differentiated this expression of theta and then we evaluated this differential at the base, means at x equal to 0. Right? So what is the differential of cos hyperbolic x? Sin hyperbolic x. What is the differential of cos hyperbolic x? The differential of cos hyperbolic x is in fact the sin hyperbolic x. And then ml minus x, of course, whatever x is. And then this differential was evaluated at x equal to 0. So if we put x equal to 0, what do we get? ml. We get ml. Plus h over mk. So we have got same plus h over mk over here. Differential of sin hyperbolic x would be cos hyperbolic x. Right? And then of x and whatever x is ml minus x, and we had evaluated it at x equal to 0. So therefore there is no x over there. So therefore it is only ml. So therefore it is only ml. Did we differentiate the denominator? No. So the denominator is unchanged. Right? And how did we come up with this expression of theta over theta b for insulated tip from general case? We just did not write the second half. Over here we will do the same thing. We will not write the second half. We will not write this thing over here. So what it would be? It would then be sin hyperbolic ml over cos hyperbolic ml means tangent hyperbolic ml. So in fact this expression is coming from here and this expression is coming from here. So all you need to do is focus on the first expression. And even in the first expression you only need to focus on the numerator because the denominator is the same as numerator without an x. And even in the numerator all you need to do is focus upon ml minus x because it would be h over mk sin hyperbolic of the same thing, ml minus x. So now you would have realized that keeping track or remembering those expressions by heart should not be any problem for you. You should try to do that. It is quite interesting. So that is all the theory about or almost all the theory about the fins. And there are a few topics here and there such as corrected length, fin effectiveness, fin efficiency, etc., etc. We will be discussing those while solving the numericals and after it.